Chapter 4 is entirely about quadratic functions, and the nice thing is you guys have been working with quadratic functions ever since Algebra 1. You did an entire chapter on it. You didn't really realize that you were working with them probably, but you did. And then back in Chapter 2 we were working with quadratic functions a lot, and actually in Chapter 2 we did everything that we're going to be doing today in Section 1, which is nice. So this section is actually a review from not only Algebra 1, but also Chapter 2. So we should be able to move pretty quickly through this one. So this section is called Quadratic Functions and Transformations. So quadratic functions, when you graph them, graph parabolas, which is the prettiest word in all of algebra, right? And we all know that. So we learn about vertex form. And the nice thing is, if my board will draw, there we go. We've actually been using vertex form for quite a while in algebra, and you worked with it exclusively when we were dealing with transformations back in Chapter 2. So you're already very familiar with it. A parabola, first of all, is the graph of a quadratic function. It's just fun to say, and it's so fun to say that Tool actually wrote a song about it, and it's one of the coolest songs there is. I highly recommend listening to it. The graph of a quadratic function is a parabola. They can open up, and they can open down. You remember drawing those back in Chapter 2? Okay. So that's what a parabola looks like. A quadratic function graphs a parabola, okay? Quadratic functions can be written in the form f of x equals ax squared plus bx plus c. This form that you see here is called standard form. Standard form is when we write things in order from highest degree to lowest degree. So the highest degree term that we have here is the second degree term because it has the square on it, and then the first degree term because there would be an exponent of 1 on that x, and then the 0 degree term because there is no variable on that term. Okay? Highest degree to lowest degree is standard form. This is written in standard form, so we call it standard form. Okay? That is how we write quadratic functions. Got it? Okay. But earlier I was talking about vertex form up here. So vertex form is what we're going to be working with in this section. In Section 2, we're going to be working with standard form. All right? So prepare to fall in love all over again with vertex form. Vertex form is f of x equals a times x minus h squared plus k. Vertex form represents all of the possible transformations that can be done on the parent function f of x equals x squared. And hopefully now you can remember what we were doing back in Chapter 2 when we were doing all of those transformations on parent functions. What were the transformations that we were talking about back in Chapter 2? Stretches and compressions. So those were, in general, what kind of transformation? Starts with a D. Dilations, okay. What are the other ones? Translations. What kind of translations? What kinds of translations? We have two. Vertical translations, so up and down, and horizontal translations, left and right. Okay, and then what else? So we have translations and dilations. Rotations is another type of transformation, and reflections is the other type of transformation. So in Chapter 2, we were dealing with just 3 of the 4. We did not talk about rotations because rotations, if we took a parabola and rotated it, would no longer be a function. So we left that one out, and we just dealt with reflections, dilations, and translations. Okay? All right. Now, back in Chapter 2, I allowed you guys to be a little bit sloppy with the way that you were drawing your parabolas. You just kind of located the vertex and you kind of said, okay, it's going to open up or down, it's going to be skinny or it's going to be fat, and then you drew something that represented those ideas. In this chapter, you're not going to be allowed to be sloppy with your parabolas. You're going to have to be accurate. You're going to have to find some points, plot points, reflect points, and then draw accurate looking parabolas, okay? A great degree of precision. They're going to have to look good. Parabolas are actually very beautiful, and they should be pretty when you draw them. Otherwise, I'm going to mark them wrong. Those of you who had me before know that. Okay, so all parabolas have an axis of symmetry. The axis of symmetry is a line that divides the parabola into two mirror images. It cuts the parabola right in two, right down the center line vertically. The equation for the axis of symmetry is x equals h. And this h right here is not a coincidence. It is exactly the same as this h right here in vertex form. The vertex of the parabola is the intersection of the parabola and the axis of symmetry. So the vertex is always going to be sitting on the axis of symmetry. Or I could say, if I know where the vertex is, then the axis of symmetry is always going to cut directly through the vertex. Okay? It doesn't have a choice because of the symmetry of the parabola itself. So if I know that, then I know that the x-coordinate of the vertex is the same as the number that's on the axis of symmetry and vice versa. Okay? So that means that this number right here, the h that I'm looking at, is the x-coordinate of the vertex. Then all I need to do is remember that this number, this k value, is how much up or down the vertex gets moved off of the x-axis. And if I remember that, then I know that the k value is the y-coordinate of the vertex. So therefore, the vertex is at h comma k. And that's why this is called vertex form. Because when I look at this equation, f of x equals a times x minus h squared plus k, the vertex is sitting there staring me in the face. It's h comma k. These two numbers, h and k, are looking at me as I look at the equation. That's why it's called vertex form. The vertex is sitting there staring me in the face, okay, every single time. And that's why vertex form is so nice. If you're in vertex form, you can see where the equation is telling you where the vertex is automatically. And then you can look at the a value and know exactly what way the parabola opens, if it's going to be skinny or fat. You can basically graph this thing in your head. Standard form doesn't let you do that. Vertex form does. Okay? It's a beautiful form for a quadratic equation. And let me see if I have everything that I needed to talk about. Yeah. Okay, so axis of symmetry, a lot of times we're going to abbreviate that with just three letters, AOS. I'll always say AOS instead of axis of symmetry because that's too many syllables for me to say. I just can't stand it, so I'll say AOS. Okay, so our key concept down here for the parent quadratic function, we have just the parent sitting here. So the axis of symmetry and the vertex, nothing has been moved around, so the vertex is sitting at 0, 0. The axis of symmetry, therefore, is just the y-axis, x equals 0, okay? Axis of symmetry is an equation. The x equals part needs to be there. It's not just a number. We're not dilated, we're not reflected, so we just see the standard parabola. The vertex is sitting here at 0, 0. The axis of symmetry is sitting here at x equals 0. It's opening up, okay? Now, when we start moving this thing around, fine. The vertex will move left, right, up, down. We might flip it, we might stretch it, we might compress it. But it's all going to be coming from this parent parabola. Any questions so far? Okay. Moving on. So we're going to start by just looking at individual transformations. We know that A controls dilations and reflections, so we're going to kind of handle both of those at the same time here. So graphing a function of the form f of x equals ax squared. All we're going to do is stretch or compress or reflect here, okay? So where is the vertex going to be? At the origin, yeah, 0, 0. I don't see an h and I don't see a k, so it didn't move anywhere, right? So the vertex is sitting at 0, 0, which means I can mark it right away. And I've really been having some problems with my board today, so I'm probably going to wind up like throwing it in the lake. For these functions, there is a dilation and or reflection, but no translations. Plot the vertex, plot the axis of symmetry. We know the axis of symmetry is going to cut directly through the vertex vertically. So we draw a dotted line through the vertex. And then you're going to want to make a little table and pick a couple of points. Okay, so we're always going to make like a two-column table here unless we have a super complicated looking equation, but none of these equations are going to be super complicated, and I'll show you why here by the end of the period. And then 2 easy points on one side, not both sides, just one side of the axis of symmetry. So go with the easier looking side, which means we can go with numbers like positive 1, 2, 3, 4, 5, or negative 1, 2, 3, 4, 5. What numbers sound easier to you? The positive ones, right? But we want to pick smart numbers on that side. So taking a look at our equation, what are the smart numbers on that side going to be? Why even numbers? Because of the 1/2. We need to choose numbers that are divisible by 2 because of the 1/2 sitting out front. Okay? Those are smart numbers. So what numbers am I going to put in my table? Well, I'm not going to choose 0 because I already have 0, 0 as a point. So just 2 and 4. I might need 6 also, but for right now, just 2 and 4. Okay? So I plug 2 in, and what do I get? 2 squared is 4, and then times 1/2, 2. And then 4 squared is 16 times 1/2 is 8. Now, keep in mind what your scale is here, okay? We only have 7 lines on the y-axis, right? We're now at 8, which means we're off the grid. So there's no more need to go any farther than that. We don't need to change the scale. I don't want to change the scale, all right? We're done. That's all we need. So plot those points. We have 2, 2, and we have 4, 8. Now 8 is off of the grid, and that's okay. That's actually what we want. So we go to 4, and then here's 7. So then we go up a little bit more, and we imagine where 8 would be. See, I'm having these problems with this board today. I'm really struggling. Okay, we're just going to imagine there. Okay, so now I have some dots, right? So what we're going to do is we're going to use this idea of symmetry with the parabola and reflect those dots over the axis of symmetry, okay? Now, for those of you who haven't had me before, you didn't have me for Algebra 1, you didn't go through this idea of what it means to reflect, okay? So imagine you're looking at a mirror. You're probably looking into a mirror this morning when you're getting ready for school, right? What did you see when you looked in the mirror? You saw me, right? I was looking at you. No, you saw you, right? But where were you? You were in front of the mirror, but where was your reflection?
In the mirror.
In the mirror, but where? Like your nose was smashed into the mirror? On the other side?
Like standing back up, being just like I was.
And then it's like where the mirror is.
Like right there, smashed into the mirror.
No, back the same amount from where you were standing.
The same distance away, but you're floating off over to the side, to the left a little bit, maybe.
What?
Yes, definitely.
What am I saying? Give me a word in geometry that would describe this.
A dom? I don't know.
Oh, you can't use the word that is the definition of what you're trying to define, though.
What? Why not?
It's in the same distance.
Same distance away, so equidistant and... Say it louder then. What is this?
Perpendicular.
Perpendicular to the mirror, okay? So directly into the mirror, what do I see? I see me directly on the other side. We're perpendicular to the mirror, right? So I need to go perpendicular to my axis of symmetry, and then I need to go whatever distance I was away from my axis of symmetry. So perpendicular to my axis of symmetry here, I went 2 units. So I'm going to go 2 units again on the other side, right? That's how you reflect these dots through the axis of symmetry. So I go 1, 2 units, 1, 2 units again, and I make my dot. Now this dot up here, there we go, is 4 units away. And even though my dot is kind of in a kind of floating off in space, I know that I'm 4 units away. So I'm going to go 4 units away again and make my dot over here. And now here's the power of what we're doing. We knew where the vertex was just because of vertex form, okay? So that point we got for free. We did a little bit of work to get these 2 points, here and here. on the right-hand side. And then we used reflection, we used the idea of symmetry to get the other 2 points. So really we did a little bit of work to get 2 points, and the other 3 points in this parabola we got for free. And that's what we're going to be doing. That's the power of transformations and using symmetry here. Most of the time in this section with vertex form, we're going to be doing a little bit of work and getting a ton of stuff for free. Okay? Now draw your parabola. These 2 points that are above the grid line are really helpful for us because they're going to allow us to draw a really good-looking parabola without screwing it up and making it look ugly. And I'll talk about ugly-looking parabolas here in a little bit and what you shouldn't do. So we draw a nice smooth curve. Notice I said right there, smooth curve. I don't know how that happens. Draw a smooth curve here and then arrows on the ends. So we want to go, it's not drawing. Okay, it's still not drawing. Come on. There we go, maybe. Draw. Draw something. It's still not drawing. There we go. I don't believe it. That's like the worst looking parabola I've ever drawn. It's not my fault, I promise.
So you think we can draw one better?
Yeah, you better draw one better because that thing looks terrible. I can't even stand it. I'm not going to be able to look at that.
It might not be better, but my God, it's there.
It's still not great.
How about that?
That's pretty good.
The greatest parabola.
Don't cover up your parabolas. I can see them from all the way on the other side of the room. I know when they're terrible. Okay, let's do the other one now. Maybe this one will go better, and I won't have to explain it for 20 minutes. What do we do? No?
Find the vertex.
Where's the vertex? It's at 0, 0. I know that because I don't see an h or k value. Now what? No.
Oh, now you draw your axis.
Axis of symmetry is where?
The y.
Yeah, it's going through the vertex. So I can draw that on there. Now, while I'm doing that, I might as well picture what this parabola looks like. What is it going to look like?
No.
It's going to open down. That's right. How do I know that?
It's negative.
Because of the negative a value. What else do I know about this parabola? It's going to be fat because of the compression value of 1/3. Okay? Got squished. So now what do I do? Now I can make a table. So I have x and y. I really only need 2 columns here. So I got to choose some numbers. What numbers do you want to pick? 3 and 6. Why are you choosing those numbers? Because they're divisible by 3. Why negative? It's not going to make a difference. 3 and 6. When we square it, it's going to become positive anyway. But it was a good thought. Okay, so I take 3 and I square it. I get 9 times negative 1/3. Negative 3. And then I take 6 and I square it. Okay, times negative 1/3. Negative 12. Now, where is negative 12? Just off the grid or way off the grid? So it's way off the grid. Now, that means we have a couple of choices here. We could imagine where negative 12 is and draw that point. We could change the scale and then have a point to plot because we changed the scale. Or we could make another point here, okay? And then just deal with the fact that we have to plot something with a fraction on it, all right? This 12 is really not that great of a number to try to plot, okay? So that second option is the one I'm going to go with because I need something a little bit better than this negative 12, all right? So I'm going to go with 4. I just need something better than negative 12 is what I'm saying. So we put 4 in. 4 squared is what? So then 16 times negative 1/3 is going to be negative, obviously. 16 thirds. If I made that a mixed number so that I can graph it easily, it would be 5 and a third. Good. Negative 5 and 1/3. That's not super tough to graph. We just don't really like working with fractions. We try to avoid it if we can. So now we can graph these. We have 3, negative 3. Then we have 6, negative 12. So here's negative 7, negative 8, negative 9, negative 10. It's way down here somewhere, right? It's terrible, but I'm going to put it on there anyway. And then 4 and then -5 1/3 is like somewhere in here. Now what do we do? Reflect them. So just count as you go. So we have 1, 2, 3 units to reflect. So 3 units again. We got our dot. 1, 2, 3, 4 units. So 1, 2, 3, 4 again. And we put our dot. And then this one way down here is 6 units. So 6 and then 6. And it's a really just total guessing game down here. And the only reason I'm putting it down there is to make a point here in a second. Ordinarily, I wouldn't even bother with those 2 that are way down there. It's actually like a really bad idea to do that. Okay, now what do we do? Now we try to make a smooth curve. Draw your parabola in there, arrows on the ends. The rule for the parabola is it has to go all the way through the grid and arrows on the ends. Just like when we draw a line, the line has to go all the way through the grid with arrows on the ends. Okay? The parabola is not going to be just a little fingernail on the grid, and that's it. It has to go all the way through the grid. Okay? So this is bad. This one right here, we're not doing that. I have a bunch of other terrible examples that I'm going to show you that I don't want to see because I will mark them wrong and or throw up all over your homework. Ready? Parabolas do not loop in on themselves. Parabolas extend outward and upward for forever. They're functions. This is not a function. This would not pass the vertical line test. Okay? Parabolas do not go vertical. They are not U's. They're not staples. Okay? They extend outward and upward for forever. They also do not curl outward like this. That's not a parabola. That's a vase. Okay? We do not play connect the dots with parabolas. This isn't second grade. We draw smooth curves when we make our parabolas, like when you're driving a car. Okay? Parabolas are not V's. Draw, draw, draw something. There we go. That's not a parabola. That's an absolute value graph. I don't know what's going on with the board today. Okay, that's absolute value. That is something beautiful. Okay, this is terrible. This is beautiful. Know the difference. Got it? Okay. Things that are lumpy. That is clearly garbage. Okay, don't draw that. I'm not even going to comment on what that is. You're just going to get a char mark on your homework if it even comes back to you. Don't do that. One other thing that I want to point out. If you try to draw your parabola and you wind up with a point, if you look at what you drew just now and you have a point at your vertex, if that's you, then what you're doing is actually a really simple thing that you can fix. So let me draw a couple of points on here. I'm going to try to draw a couple of points on here. Now, when you try to draw your parabola, what I'm talking about is this. You're drawing and then you just, everything is nicely curved, but then right at the vertex you kind of got stuck and you wound up with a point. Okay? If that's you, what you can do instead is just picture when you're driving your car and let's say you're trying to make a left-hand turn. When you were learning how to drive, you probably were cutting that turn off a lot, right? And what you found out is that you had to pull out farther. Like when you're making your left-hand turn, you just drive out into the intersection a ways first, and then you start to make your turn, and then once you figure that out, then the left-hand turn was a lot easier, okay? If you don't know what I'm talking about yet, you probably don't know how to drive yet, or you're just cutting people off all the time and you're a terrible driver. If that's you, all you got to do is just drive out into the intersection a little ways farther and then start your turn, and you'll become a better driver, okay? Just try it today. Do the same thing here, okay? If you're making this sharp point right here and you can't figure out why, all you need to do is drop your pencil down a little bit farther before you start to head over to the vertex. And that will help you round off this vertex right here, and you'll start to make a much nicer looking rounded area like you see over here on this guy. Okay? Those are my tips. So don't give me this crap up here. These are all just junk. Practice drawing parabolas and eventually you'll get good at them. Okay? It's like a huge pet peeve of mine when people give me crappy parabolas. Obviously, I just spent 5 minutes talking about garbage. Okay? Are we ready? Okay. So, let's continue on, and hopefully my board will cooperate. So, that was graphing, and all we were talking about was dilations and reflections. Okay? Now we're going to move on to vertical translations. So we have this plus k situation going on. All it does is move the parabola up or down. Okay? So the k controls the vertical translations if I want to use proper vocabulary. The vertex is now going to be at 0, something because we moved it up or down. If I see a plus k, I moved it up. If I see a minus k, I moved it down. Plot the vertex, the axis of symmetry, and then easy points on one side or the other of the axis of symmetry, just depending on which points you think are going to be easier to work with. And then reflect and draw a smooth curve, just like we were doing before. Okay? Really easy stuff. So, f of x equals x squared minus 5. Which way did we move this thing? Down. How far? 5 units. So where's the vertex at? Yeah. So we put our vertex on there at 0, -5. Where's our axis of symmetry? Going through the vertex. So we put the dotted line on there. And then what do? Make our table. X and Y. We only need 2 columns because these are super easy. Now what? What numbers? Yeah, 1 and 2 is going to be great because we don't have a fraction to worry about this time. Now, the one thing I will say is which way does this parabola open? Up. It opens up. And because we dropped the vertex way down to the bottom of the graph and it opens up, chances are pretty good we're going to need at least one more point because these 2 points are going to give us something kind of lower than the top part of the graph. And I need something up high so that I don't wind up drawing something stupid, like making the parabola curl in on itself or curl out on itself, making it look like a vase, okay? I just spent 5 minutes telling you how to not draw a parabola. I want to make sure that I have a good number of points so that I draw a good-looking parabola, okay? So for sure, I need 3, and I might even need another point after that. I might need to figure out what 4 gives me, okay? So just keep that in mind. So if I plug in 1 now, what do I get? -4. If I plug in 2, what do I get? Okay, yeah, 2 squared is 4, minus 5 is -1. He sounded unsure. So if I plug in 3, what do I get? Yep, 9 minus 5 is 4. Now, does that take me to the top of my grid? And I'm far enough away that I'm a little nervous. I might try one more point. So if I plug in 4, what do I get? 11. Now, that's clearly off of my grid, right? I probably don't really want to plot that point, but I'm going to use it as something to shoot for as I'm drawing my parabola so that I don't accidentally draw something dumb. Okay? All right. So we plot these points now. We have 1, -4, and then 2, -1, and then 3, 4. And then 4, and then 7, 8, 9, 10. So that's probably like right around here. And like I said, I'm not really plotting that point. I'm just kind of making a mark to give my eye something to see so that as I'm drawing my parabola, I have a target to try to shoot for as I'm getting my parabola to go outside of the grid. Now, what do? Reflect all these points. I can't wait to watch this thing float down the river. It's going to be awesome. Okay. Now what? Draw the parabola, okay? Now, I'm not really starting at this dot, but what I am doing is kind of like tracing my hand from this dot down to where I'm closer to the grid, and then I'm starting there, okay? And then I'm going to work my way around drawing a smooth curve, and as I exit the grid, headed towards this last dot, then I'm going to lift my pencil off the paper so that I'm not drawing this ridiculously long outside of the grid parabola. Does that make sense? So here I go. And I'm done. wonder if it floats. Yeah, that's what I'm wondering. Like maybe we could raft down the river with it. Right. Could be fun. Okay, let's try the second one.
Potentially. That has potential.
Let's try this one. What do we do? Okay, so the vertex is going to be where? Yeah, 0, 3. Okay, now what? The axis of symmetry goes through that. Now what? So xy, 2 columns, and what do you want to use?
1, 2, 3.
Well, okay, so 1 and 2. Now, this one's kind of the opposite, right? Which way does this open? It opens up, and the vertex was already pretty high. So how many points am I probably going to need here? Just probably 2, and that's going to take me off of my grid. So 1 and 2 is going to do it. So if I plug in 1, what do I get? 4. And if I plug in 2, 7. And 7 is already the top of the grid, so there's no need to do any more. So I plot those, 1, 4, and 2, 7. And then I reflect them. And those dots are all automatically going to take me outside of my grid. So I just go ahead and draw in my smooth curve, or try to anyway. Oh my God. And we're done. Hers are better.
I know. I don't need to be told I'm not enough.
Yeah, I agree.
Well, thanks for making me feel really good.
Okay, we ready? So we've done the A and the K. Now we're going to move on to the H. H controls the horizontal, yeah, the left and the right. This one is the tricky one. Remember, we're supposed to see the minus sign. So when I see the minus sign, when I see x minus a number, which way are we going?
Right.
We're going to the right. And if I see x plus the number, really what I have is x minus negative something, which means we're going to the left, okay? So keep that in mind. If I see x plus, it's really x minus negative h squared, okay? That's the tricky one. Please keep it in mind, because if you screw up a horizontal translation, the whole thing is going to fall apart if you're depending on your transformations to get you through these problems, all right? Okay, so the vertex is going to be at h comma 0. Plot the vertex, axis of symmetry, easy points, and reflect and draw a smooth curve. So it's the same thing as before. So where am I on the first one? Right 4. X minus 4 squared moves me to the right, because really that's a positive 4 for the x coordinate. So here I am at 4. Now what? Axis of symmetry goes through that vertex. Now what? Make your table, same as before, x, y. Now what? Pick points. We can always go to the right or to the left of the vertex, but not both. So we can go, we're at 4, so we can go 5, 6, 7. We can also go 3, 2, 1. Which way would you rather go? 3, 2, 1, fine. It doesn't make any difference, okay? It's just whichever numbers you are more comfortable with. Let's go 3, 2, 1. Even if you don't like it, let's do it that way, just to show you that we can do it that way. So now we plug in those numbers. I plug in 3. 3 minus 4. Negative 1 squared, 1. Plug in 2. 2 minus 4. Negative 2 squared, 4. Plug in 1. 1 minus 4. Negative 3 squared, 9. Now 9 takes us off of our grid, but that's okay. That's like what we want, right? Because now we have something to shoot for that's off of our grid, and we won't have a fingernail-looking parabola. We'll have a nice-looking parabola. Okay, so now what do we do? Plot the points. So we have 3, 1, we have 2, 4, and we have 1, and then 7, 8, 9. So we kind of guess at where that one is. We try to graph the point. There we go. Now what? Okay, reflect them. And And then draw your smooth curve. What? Yeah?
He can smell it.
Ready for the last one? Where are we going? Left one. So there's our vertex. And then what? Axis of symmetry, dotted vertical line. Yeah, that's what we do. Because it's not really on the graph, so we do a dotted one, so it's not like it's part of the graph. Table. Now what? I like the 0, 1, 2 because 0 is an easy number, so is 1, and really so is 2, okay? Easier to go to the right this time. So plug in 0, what do you get? 1. Plug in 1, what do you get? 4. And plug in 2, what do you get? Okay. Now what? Plot them. 2, 7, 8, 9. And then reflect them. And then draw in your parabola. So we have a little summary of all of our transformations. We can put all of these together. So those problems that we were doing takes each transformation individually, but we can handle all the transformations all simultaneously. So here's a summary of all of them. Here's vertex form again. F of x equals a times x minus h squared plus k. A controls dilations. So if a is greater than 1, what kind of dilation do we have? It's a, what kind of stretch? Vertical stretch. And then you were kind of on the right track with your description. How will the parabola look? Yeah, parabola looks skinny. Okay, and if a is between 0 and 1, that's how you would read that. What do we have? Vertical compression. And how will the parabola look? Parabola looks fat. Good. But A also controls reflections. So if A is positive, so positive A, what happens? Opens up. And a negative A, parabola opens down. So in other words, opens up means my parabola will look like this. Opens down, my parabola will look like that. Okay, H controls horizontal translations. Horizontal translations means if I see in the parentheses x minus some number squared, the parabola shifts which way? That's correct, to the right. And if I see in parentheses x plus some number squared, the parabola shifts left. And again, the x plus h squared is really x minus a negative number. Okay, K also controls, or sorry, not also, but just controls vertical translations. So if I see stuff in the parentheses and then outside of that some number, so plus some number, what happens? So plus some number, which way did I go? I went up. And then I see some stuff squared and then minus some number. Which way did I go? Yep. Down. So that's a summary of the transformations that we actually learned back in chapter 2. And now we're using officially here in chapter 4. And now we're going to put them all together. So, here we go. You can apply the constants of vertex form to help you graph the parabola, but you may not just sketch the graph without finding at least 2 additional points to assure accuracy in your graph. And remember what I was talking about earlier. All the way through the grid, arrows on the ends, they can't look like trash. Locate the vertex, draw the axis of symmetry, choose 2 z-points, plot and reflect these points, then draw your smooth curve. Here's your examples. Take a look at the one on the left. Before we do anything, tell me something about this graph. Okay, it's going to open down. What else do we know? So give me the ordered pair for the vertex. 1, 3. Good. What else do we know? It'll be skinny. And what else do we know? The graph is a parabola. How do I know that the graph is a parabola? Because it's a quadratic function. The x term is squared. Okay? You got to see that. All right. So we said that the vertex is at 1, 3. So we go to 1, 3, and we make our vertex. Now what? Yep, we have an axis of symmetry, so we can put that on there. Now what? A table. Now, this function looks a lot more complicated than the other ones that we were looking at, but I still don't need to make a 3-column table because the order of operations in vertex form makes the math that we're going to be doing here actually still easy to do in our heads. Okay? So a 2-column table here is fine. Now what? Pick your numbers. Which numbers do you want to use? 2, 3, and you said this thing opens down, so I might, because we moved the vertex up some, I might need 3 points. Okay? So 2, 3, 4. Okay. Now, when I plug in 2, you just need to follow the order of operations. So we're plugging 2 inside the parentheses. Inside the parentheses goes first. So 2 minus 1. Then exponents happens. So 1 squared. Then multiplication happens. So 1 times negative 2. And then addition happens. Negative 2 plus 3, 1. Okay? Just follow the order of operations and you're going to get there. So 3 minus 1. Negative 2 squared. 2 squared is 4. And then 4 times negative 2. Okay, and then negative 8 plus 3. Negative 5. Now, negative 5 is actually really close already to the bottom of the grid. And if I plot this 2, 1, we're here. And then the 3, negative 5 is already way down here. So we had an enormous drop from one point to the next. If I try to put that 4 in, there's no way that that point is going to be anywhere near something that I even want to bother trying to graph. Okay? So I'm not even going to bother with it because I know that it's not going to help me at all. Okay? So now we reflect these. But I didn't get a point that was off of the grid, so I have nothing to shoot for as I'm getting my parabola to go outside of the grid. So I have to be very careful. I don't want to loop this in or loop it out and make it look like a vase. Okay, so what do? Well, I know that this is going to extend downward and outward for forever. So what I need to do is I just need to know that it's not going to go vertical, and it's not going to curl in, and it's not going to loop out, right? So if this were to extend downward vertically, I would end up right there. But I don't want that. If it was just outside of that mark, I'd be good, okay? So what I want to do is end up just outside of vertical and start just outside of vertical, okay? Not very far outside of vertical on either one of those. Because if I go too far, then it's going to start looking like a vase, and I don't want that to happen, okay? So when I draw this parabola, I'm going just outside of the dot on the left, and I'm going to finish just outside of the dot on the right. And see, that was terrible. Just outside of the dot, just outside of the dot. And you're done. It takes practice. Just as long as it's not lumpy and it doesn't look like a V. And you don't connect the dots. It doesn't curl in on itself or out.
It's either going to be lumpy or connected.
And it otherwise doesn't look like trash. Okay, let's look at the next one. We're getting close to being done, by the way. Look at the next one. What do we do? Tell me something about it. Opens up, okay.
It's going to be vertical.
Fat, yes. It's fat because of the 1/3.
It's going to be to the left here.
It's a parabola, good. Left 2, down 4. So where's the vertex? -2, -4. So we can mark that. It opens up and it's going to be fat. Now what? We have an axis of symmetry going through that vertex. Okay, now what? Make your table, all right. What numbers to pick? No. Okay, that's a good thought. We have that 1/3 sitting there, so we want numbers that are multiples of 3. But I'm not going to write down 3 and 6 because those numbers won't work. 1 is a good number. And 2 is a bad number. 4 is a good number. How come 1 and 4 when I'm worried about this 1/3 out front?
Because you're going to add 2.
Yes. Inside the parentheses, we're going to add 2. So I do need a number that's a multiple of 3, but after I take care of what's inside the parentheses. Before that, the number is not a multiple of 3, okay? But 1 plus 2 is 3. That's what needs to be a multiple of 3, okay? Very good. Sometimes it takes classes a little while to figure that one out. So 3 squared is 9. 1/3 of that. 3 minus 4, -1. And then 4 plus 2 squared. 36, 1/3 of that. 12 minus 4 is 8. 8 is off the grid, so we're done. We have 1, -1, and then 4, 8. That's the best we can do with this situation. We reflect. Okay, and then this one, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5. Total guessing game on that point, but that's okay. And then we draw in our parabola. Okay, we're almost done. All parabolas have either a maximum or a minimum value, and they will always occur at the vertex. Minimum values occur when the parabola opens upward at the vertex. If you draw a picture, you'll see why. If the parabola opens up, it looks like that. It has a low point. It has a minimum value. And the minimum value, the low point, is at the vertex. If the parabola opens up downward, there's a high point. There's a maximum value. And it occurs at the vertex. In both cases, whether you have a minimum or a maximum value, in both cases, it's the y coordinate of the vertex. So if you want to know what the minimum is or the maximum, you would find the vertex And then you would say you have a minimum of or a maximum of, and then whatever the y-coordinate of the vertex is. And you're done. Okay? It's really actually very easy. Now, it says go back to the previous examples and identify the vertex, axis of symmetry. So we know how to do the vertex. We know how to do the axis of symmetry. Maximum or minimum value, we just learned how to do that. And then this domain and range situation. Let me talk about domain and range. Domain is always x values. X values that work. Meaning the x values that you can plug in, let me make that look like an R, x values that you can plug into the function and you will actually be able to get an answer for, okay? With these parabolas, there is not a single number out there that you don't know yet that you can't plug in, which means that every single number works. And if that's the case, then the domain is going to be all real numbers for every parabola that we work with. The range is all of the y values that get graphed. Now, a parabola turns around on itself, which means some y values are going to get graphed and some y values aren't going to get graphed. If you look at a parabola, let me draw one here. If the parabola opens up, then there's going to be some y value that starts the getting graphed part, and then if it opens up, every y value above that is going to get graphed. Okay? The lowest y value and higher is getting graphed if the parabola opens up. If the parabola opens down, the highest y value and down is going to get graphed. Okay? What is the lowest or highest y value? The y-coordinate of the vertex. Okay? So all you need to know is the y-coordinate of the vertex and which way the parabola opens, and you'll be able to describe the range. So let's go back and see if we can describe some of these. Let me pick a winner here. Yeah, let's go back to this screen. And a color that's going to be fun. Raspberry sorbet. I'll go to the one on the right side because the other one's way too cluttered. Let's just do this one. So it's asking us for the vertex. So let's just label vertex. What is it? 0, 0. And now axis of symmetry, I told you I'm going to abbreviate that AOS. And that is an equation. It's x equals, it's not just a number. X equals what? 0. The number that the axis of symmetry goes through. It's always the x coordinate of the vertex. Now, do we have a maximum or minimum in this case? The parabola opens down, which gives us a peak. That's a maximum. So we have a maximum of what? 0, the y-coordinate of the vertex. So it's a maximum of 0. Now, what's the domain? Are there any numbers for x that we cannot plug in? No, every single number that there is works. The domain is always going to be all real numbers for these parabolas. And now the range. The way that you're going to write the range is you're going to say all the y values that are getting graphed. Since this thing opens down, you're going to say less than or equal to. And what's the biggest y value that's getting graphed in this case? It's the y-coordinate of the vertex, 0. Let's do the next one. Let's do the one on the right again. So, vertex. What is it? 0, 3. Axis of symmetry, AOS. X equals 0. Okay, what's next? This is a minimum because the parabola opens up, so it's a minimum of 3, the y-coordinate of the vertex. Now, what's the domain? It's always going to be all real numbers. And what's the range? Y is greater than or equal to this time because the parabola opens up, and it's the y coordinate of the vertex, 3. Okay? So let's skip ahead, and we'll skip these guys. Let's go on to the really interesting ones, these two here. Let's do both of these, and we'll see if we're good. So the one on the left, first, vertex. Vertex is 1, 3. Axis of symmetry. X equals 1. It is an equation, not a number. Okay, next. This opens down, so it's a maximum of 3, the y coordinate of the vertex, the highest number that there is in the range. Okay, domain. All real numbers. Now the range. Y is less than or equal to 3. Good. And this last one, vertex. Okay, -2, -4 is right. An axis of symmetry. X equals -2. And then minimum of -4, the y coordinate of the vertex. Make that look like an of. Okay, and then is what? Domain is all real numbers. Range. Y is greater than or equal to -4 is correct. So that's how you call out all of those things. Okay? And that's it for this section. We're done.